Did I? No. Now I did. All right. Well, if you need a brief reminder and introduction to the Diels-Alder reaction that I just gave those of you who were here today, just go to the 8 a.m. lecture and you can hear what I just said. Hey, it's better than, at least we're recording audio today, right? Like, all right. So let's see. I want you to pay attention to the fact that when the diene is in the S-cis conformation, there are two different environments for the substituents or groups that are on carbons 1 and 4. You have groups in blue that are pointing inward, and you have groups in green that are pointing outward. Okay. Similarly, pay attention to the fact that on the olefin, why did I choose pink? I meant green. Oh well. On the olefin or the dienophile, you have groups that are pointing upwards and groups that are pointing downwards. Why are we doing all of this? Well, those issues are going to be important later on when we consider stereochemistry. So I just need you to be used to thinking of those things. Yes?
Is there any similarity between these and chair conformations?
Any similarity between these and chair conformations? Technically, the cyclohexene ring that you form could form sort of a chair. People know about that, and they've talked about it, but we won't. All right, so when the diene and the dienophile react with each other, they can approach from this side or that side, okay? And there's another feature, and it doesn't matter for this particular choice of diene and dienophile, but somebody out there will want to know it and ask me about it. If you flipped it, what if this were carbon 2 and this were carbon 1? In other words, what if you flipped the diene over? For more complicated examples, what we just did is going to be the difference between two regioisomers. That is connectivity, whether you make a bond between orange 1 and purple 1, orange 1 and orange 4 and purple 2, or whether you make a new bond between orange 1 and purple 2 and orange 4 and purple 1. We're not going to be doing that today or ever. Okay, we're not going to be considering regioisomers in the Diels-Alder reaction. So I'm going to punt on all questions about what if the diene, what if the olefin got flipped over so that you made a different set of sigma bonds. We will deal in detail with all the stereochemical issues though. All right, of course here, both the diene and the olefin are symmetrical, so even if you flipped, you get the exact same thing, right? You with me? I know I'm going through this fast, so yes? Okay. Now, in the reaction, as the olefin approaches the diene, let me illustrate the new sigma bonds that we're going to make. We're going to make a new sigma bond between orange 4 and purple 2, a new sigma bond between orange 1 and purple 1. We're going to break this pi bond, and we're going to make a new pi bond between 2 and 3. The dotted red lines, which I will now just, I'm going to add orange highlighting for the diene. I'm going to add purple highlighting for the olefin. And then I'm going to highlight in gray the whole cyclohexene ring that we form. Okay? That's the transition state that leads to the Diels-Alder reaction. Now, I need you to notice a couple of things. First, notice that the two groups that are blue that we're pointing inside in the S-cis conformation of the diene, blue is the inside group, green is the outside group. Notice that the two blue inside groups end up on the same side of the green cyclohexene ring. In other words, if I draw the product here, and I know we're just dealing with protons, I know you can't actually tell that this is the case, We're starting simple, we're gonna get more complicated. But I didn't do this at 8 a.m. and I wished I had. The two blue protons that used to be pointing inside in the S-cis conformation, they end up cis to each other in the new cyclohexene ring. The two protons that were pointing outward end up cis to each other as well, but trans to the blue protons. Okay? So that is a stereochemical rule in the Diels-Alder reaction. It's an element of stereospecificity. Oh, goodness. Stereospecificity. I'm doing Duolingo, trying to learn some Portuguese. My mission language was Spanish, but it was American sort of Spanish. But anyway, I'm trying to learn Portuguese because it seems pretty easy. But I just learned a word for blender that's like almost impossible to pronounce. Liquidificador or something like that. What a pain, right? Stereospecificity is much easier to say. It rolls off the tongue. Anyway. Do I remember the word for blender in Spanish? No, I don't. I never learned it. I never had to. So one rule for stereospecificity with respect to the diene is outside groups are cis to each other in the Diels-Alder product. Inside groups are cis to each other in the Diels-Alder product. And importantly, outside versus inside groups are trans to each other. Has to be that way, okay? Now, there is an element of stereospecificity related to the dienophile. And that is cis groups on the dienophile have to be cis in the Diels-Alder product, and trans groups have to be trans in the Diels-Alder product. Now, I know that with the example I've chosen, you really can't tell. Protons is protons, right? But these two pink protons are cis to each other in the Diels-Alder product. They have to be. Okay? Now, you will see. Does it make any sense at all that we're going through these stereochemical issues when all we've got is protons to deal with? The colors are okay, yeah. All right, now there's one other potential option. Of course, there were these other protons on the olefin that I didn't highlight, okay? Now, the final issue of stereochemistry for the Diels-Alder reaction is one of stereoselectivity. It's not obvious here, but this has to do with the relationship basically between the blue group and the pink groups. In other words, even though it doesn't make a difference in this particular example, you could imagine a situation where the pink protons are the ones that are wedges and the other unlabeled protons are the ones that are dashes. I said that exactly backwards. Please forgive me. You can imagine a situation where the pink protons are dashes and then the other protons are wedges. Notice in the option on the left, the pink protons are on the same side as the blue protons, whereas on the option on the right, the pink protons are on the opposite side of the ring as the blue protons. Yes?
When would that happen? When it's going from the other side, or?
So we would get that if, copy, paste. We would get that option if we flipped the diene file over such that these were the pink protons. We aren't doing flip left and right, where orange 1 goes to purple 2. Okay, yes?
So if it's back from the other side then?
So if we attack from the other side, we're going to get, if these are chiral, attack from the other side gets the enantiomers.
So blue and green is flipped, right?
Yeah. Yep. Okay, so that's mapping out the stereochemical issues. The other, and we're going to do this with examples, but before we do, yes?
So the relationship between blue and pink, they can be cis or trans? Is
That's
that what
right.
you're getting at? Okay.
Yeah, the relationship between blue and pink can be cis or trans. In certain situations, one will be preferred over the other, and I will illustrate that. Yes?
So is that like endo and exo?
Yes. If you've read about endo and exo, that's the stereoselectivity issue is always the relationship between blue and pink. Yes?
Because I was getting a little confused on the difference between like enantiomers and exo and endo.
Yes. We'll talk about that. Yeah. What is we will see that in some cases it's impossible to assign endo versus exo, and I'll show you when you can talk about it. But endo and exo is always an issue of diastereomers. Yeah. Okay. Now, we need to do some examples, but real quickly, I just want to tell you what the MO theory picture of things are. So far, we've talked about the stereochemical issues, but without examples. So put pause on that. Let me show you what's going on in terms of the MO picture of the Diels-Alder reaction. As I said, this is the one reaction we've ever dealt with where you can't pick a nucleophile and you can't pick an electrophile, because you're going to see that the HOMO of the diene attacks the LUMO of the olefin at the same time as the HOMO of the olefin attacks the LUMO of the diene. Okay, we're going to draw the diene on its side. I'm going to omit any pi bonds to try to keep our drawing simple. The HOMO of the diene, as you recall, is this pi 2 orbital. We talked about this last time. The pi 2 orbital basically looks like this. There is one node, and therefore you can see that the wave function sign on carbon 1 is opposite the wave function sign on carbon 4. So if I draw that on this sort of sideways perspective, it's a little complicated. There's going to be some overlap. Just going to have to do your best to visualize, and I can't draw 3D on 2D paper. Not very well anyway. So this is atom 1 of the olefin, this is of the diene, this is atom 4 of the diene, this is the HOMO. And importantly, if you look at the left or the right-hand side, notice that the color on carbon 4 on the right-hand face of the diene is opposite. We call this orbital, as a result, we call it anti-symmetric because the wave function sign or color is opposite on one side versus the other. Interestingly, I'm just going to draw the now, so that's the HOMO of the diene. The LUMO of the olefin should be the pi star, which is an empty orbital. And when we've drawn the pi star before, it's looked like this. There's one node in the middle. The pi star of the olefin, like the HOMO of the diene, is also anti-symmetric, meaning that on the left-hand side of the olefin, the wave function signs on purple carbons 1 and 2 are opposite. That matched symmetry of HOMO and LUMO allows them to approach each other with overlap of orbitals with the same wave function sign. Okay? So the new bond that we get, one of the new bonds that we get comes from simultaneous overlap of HOMO and LUMO on both carbons 1 and 4. Which sigma bond is represented by that? Which sigma bond comes from attack of HOMO of the diene on the LUMO of the dienophile? The answer is we can't tell because it's happening at two places at once. Okay? So this is a case where you're not going to have a clear direction analogy. This HOMO attacking this LUMO leads to this sigma bond because you've got two things happening at once. I'm talking about these new sigma bonds. Which one? You might want to know, does this one come from the HOMO of the diene and this one comes from the HOMO of the dienophile? And the answer is I don't know. Nobody does. Okay. At the same time, you would notice that the HOMO of the olefin, which is the pi carbon-carbon pi bonding orbital, looks like this. And it is a symmetric orbital, meaning that wave function sign is the same on purple carbons 1 and 2. And then if we draw the LUMO of the diene, it's actually pi 3, which is an empty orbital. And if you remember from last time, that pi 3 orbital has two nodes, and we drew it like this. And like the pi carbon-carbon pi bond of the olefin, the wave function sign on carbons 1 and 4 of the diene is identical. So if we were to draw this sort of from the side, again, it's really kind of hard to do, but we'll do the best that we can. Wave function sign on carbons 1 and 4, orange 1 and orange 4, are going to be identical to each other. And this orbital has two nodes. So that when the HOMO of the olefin attacks the LUMO of the diene, again, you have in-phase correct wave function sign orbital overlap on two places. Okay, that's where the two new sigma bonds come from. So I need you to understand and know that we get the sigma bonds in the Diels-Alder product from HOMO of the diene attacking LUMO of the dienophile and vice versa. We won't know which sigma bond comes from which, but that's where the two sigma bonds come from. Now, there were three things going on in the Diels-Alder reaction. One of them was that a pi bond ends up between carbons 2 and 3. That actually doesn't really involve any bond breaking, though the arrows seem like it should. If you think about the pi 1 electrons in the diene, these are the ones that are in this orbital that's extended over atoms 1, 2, 3, and 4. And those atoms are going to become the carbon-carbon pi bond between 2 and 3. Carbons 1 and 4 rehybridize and aren't part of the conjugated system anymore. And left behind are just those orbitals on carbons 2 and 3. And that's where that pi bond between 2 and 3 comes from. So that's the MO theory picture. Questions about that? Yes?
So the pi bond is kind of just moving where it has room, the orbital?
Yeah, it's almost like
Resonance?
it looks like you're breaking a pi bond and it's moving over. But in terms of the MO theory picture, what's happening is the two atoms 1 and 4 are rehybridizing and disappearing from the pi system. The electrons that used to be spread out between 1, 2, 3, and 4 are now just coalescing to be between 2 and 3. Yep. Yes?
So I don't know if it's going to be the same for all the Diels-Alder reactions, but especially with the diene. So pi 1 is the reformation of the new pi bond in the product. Pi 2 is where the HOMO attacks the LUMO of the olefin. And then pi 3 is the LUMO, or it is the LUMO that's being attacked by the HOMO.
That's right.
Olefin. That's always going to be true.
Yep.
with the Diels-Alder.
Yep, that's always going to be true in the Diels-Alder reaction. Good. Yes?
How might you test this on this specific?
Ah, there it is. How might I test you on this specifically? Well, take a look at the problem set. I ask you to explain for me the MO theory picture of the Diels-Alder reaction. So I could write a multiple choice question that says which of the following best describes what's going on in the Diels-Alder reaction. I also tend to ask questions about pi type orbitals like I showed you last time. Which of these is the HOMO? Which of these is the LUMO? Okay, now let's go back and do some examples dealing with the key stereochemical issues, okay? And remember our framework. Inside groups on the diene end up cis to each other in the product. Outside groups on the diene end up cis to each other in the product. Inside and outside groups end up trans to each other in the product. With respect to the olefin, cis groups stay cis and trans groups stay trans. And then there's this issue of stereoselectivity where pink and blue could be on the same or opposite sides. All right, just keep all of that in mind, and I'll illustrate this with the very first example of a Diels-Alder reaction, which was discovered in 1928. So at that time, President Nelson would have been like 4 years old. So this is within the sort of scientific lifetime of the very oldest humans. So the first example was a diene called cyclopentadiene. This one is a great molecule to do a Diels-Alder reaction with because it is cyclic. There's not 2 blue inside groups, there's just one, which happens to be tethered to both carbons 1 and 4. So there's one inside group, and it is constrained. It has to be in the S-cis conformation. It can't get to the S-trans conformation. So this one's ready to go for the Diels-Alder reaction. And they reacted it with this olefin. And it was a somewhat complicated olefin in the sense that it had 2 pi bonds in it, but they were identical to each other and only one reacts. So here's carbons 1, purple carbons 1 and 2. Now, I have chosen deliberately these 2 to be symmetrical. There will be no issues of enantiomers at all. If the olefin approaches the diene from the left or the right, you're going to get the exact same product. We're going to focus here on the stereospecificity and stereoselectivity issues that we talked about above. I've highlighted the blue and the green groups. Here are the pink groups. Okay, notice that the pink groups are cis to each other. You with me? So let's look at the products. The product is going to be a cyclohexene ring. And so anytime you're doing a Diels-Alder reaction, if you start by drawing this, you're on your way to the right answer. These 4 atoms of the cyclohexene ring came from the diene. These 2 atoms of the cyclohexene ring came from the olefin. If you identify the pi bond in the cyclohexene ring, you have already identified carbons 2 and 3 of the original diene. From that, you can figure out which are carbons 1 and 4 and which were carbons 1 and 2 of the original olefin. Okay? Now, because this reaction happens all at the same time, the inside groups, as I've said before, have to end up on the same side of the ring. In this case, that's obvious because there's only one inside group and it can't be in 2 places at once. So it, by definition, is on the same side of the ring as itself. But notice that the green outside groups, the protons, are indeed cis to each other, but trans to the blue group. Now, some of you are looking at this and saying, what the heck am I even looking at? I didn't know that you could have a wedge pointing towards the middle of a six-membered ring. Generally, you can't unless that wedge atom is attached to another atom on the other side of the ring. If you want to see how this would look from the side, I will draw it for you in a little bit. Now, what about the pink groups on the olefin? They have to be cis to each other, but there are two possibilities. This is one, where they are up, and then we have the other possibility, where they would be down. And if you want, at the end of the semester, you can fill out your course evaluations and explain to the department chair how much time I spend in class coloring. Right. So importantly, notice these two possibilities. Pink and blue are on the same side of the ring versus pink and blue on opposite sides of the ring. We're going to call this one exo and this one endo, but the relationship between those two is that they are diastereomers. It's always true. Now, when can you assign endo versus exo? You can only really assign endo versus exo when you have something non-hydrogen that's pointing at the inside of the diene, and when you have two groups that are cis to each other on the olefin. Otherwise, it gets really difficult. And in practice, chemists care most about endo and exo when there is a bridging atom. Some of you, I think, wanted to see what this looks like from the side. So I will attempt to draw that for you here. It's going to be ugly. There's a lot of examples of this kind of thing in your text. These are atoms 1, 2, 3, and 4. Here is the pi bond of your diene. This is the blue atom. And then this is the atoms 1 and 2 of the olefin. Hydrogens, green hydrogens, would be angled downward. And then depending on which isomer you wanted to draw, hydrogens would be, if we wanted to draw the exodiastereomer, we could sort of do it like this. That's kind of ugly. Sorry. Ugh. And these are the pink groups. Okay. All right, so endo versus exo is an issue of blue versus pink. Let me just illustrate briefly where we get the endo versus the exo products. I've illustrated it already above, but I think it's important to do it again for this example. If it's okay, I'm gonna, just to save a little bit of time, I'm gonna try to avoid labeling everything in color and just label the pink and the blue groups. So you've got the diene on the left, and on the right, you've got the olefin. I'm trying to draw it flat, and it's ugly, and I know, I'm sorry. Oops, I'm gonna highlight the two groups on the olefin. I'm gonna identify carbons 1, orange 1, and 4 on the diene, purple 1 and 2 on the dienophile. And you'll notice that again, here is the ring that we are forming. Here's the new sigma bond between 1 and purple 1, between 4 and purple 2. Here's the new 6-membered ring that we're making. And you can see that in this endo transition state, sorry, I should call it, I got it exactly wrong, exo transition state, blue and pink are on the same side. Where do we get the endo product form from? That was like a bad spell check moment. Back in the days when spell check didn't know grammar, if you wrote form instead of from, the computer would just be like, that's good to me. So again, here is the diene with the blue group here. If we have the olefin approach the diene with the protons up and the carbons down, that's where we get the endo product form from. I did it again, oh my gosh. Okay, so there's the cyclohexene ring. That's the endo transition state. Your text says that in many cases the endo transition state is favored. There is some idea that if there are pi type atoms on the substituents, the pink groups of the dienophile, that in the endo transition state they might be interacting a little bit with the parts of the orbital that are on carbons 2 and 3. It's also possible that the endo transition state is just more compact and therefore doesn't have to push as many solvent molecules out of the way, and therefore it's more entropically favorable. In any case, in Diels-Alder reactions like this, the endo isomer is preferred. On the problem set, as you have seen, I like you to draw both and then just tell me if you can which is endo versus exo. But again, you can only tell endo versus exo when you can clearly identify the group that was pointing inward on the diene and when the dienophile is cis. Okay? Yes?
Why wouldn't you worry about the blue group becoming wedges?
You could worry about the blue group becoming wedges. That, if you imagine that, that would be, if this were a wedge, but these still stayed as dashes. You got that in your mind? Flip it over, it's actually this one. Yeah. We get the alternative stereochemistries by approach from the other side, but in this case, you get exactly the same thing. But in cases where the products are chiral, that's where the enantiomers would come from. Oh, man. Yes, go ahead.
So the exo product, they're like both sides are wedges. They're that middle group and the olefins extra groups. And then for the endo, you have wedges and dashes on opposite sides. Why are they called that?
Why do they call it endo versus exo?
Yeah, I would think like that seems counter.
Where does the name come from? Great question, and I don't really know. Endo is in and exo is out.
Right.
So it's possible that they're calling this direction the in direction and that direction the out direction. I don't know. It's kind of arbitrary. Was that your question?
Yeah, I was like, how do you remember it?
How do you remember it? You need a mnemonic device. We're not even going to bother spelling that one. It doesn't start with a P, I know that. You need a mnemonic device, and I'm not sure. Endo, DO is down, so when you draw it like this, as long as you keep the blue group up, if the pink groups are down, then that's endo. DO for down, I don't know. I mean, come up with something better if you don't like it, but yeah. Okay. All right, let's do some examples. And before we finish, so we got about 5 minutes for examples and then 5 minutes for retrosynthesis. So we'll do some simple examples and then increase them in complexity. Here is a simple diene. Here is a simple olefin or dienophile. notice that I can't distinguish between the blue groups and the green groups on the diene because they're all hydrogens. That automatically tells me that endo versus exo is not going to be an issue for this reaction. But I still got to take care of the fact that the olefin has stereochemistry. Those two groups on the olefin are cis to each other. They must be cis to each other in the product. So I'm going to draw the cyclohexene ring. I'm going to remember that these two are the bonds between what used to be the diene and what used to be the dienophile. And then if I have one of the pink groups on the what used to be the dienophile be a wedge, the other one's got to be a wedge too. They have to be cis to each other. They are cis here, they are cis there. That's stereospecificity. Now, you want to ask, well, what if the groups are dashes instead of wedges? That's a meso compound. The wedge thing you just described in your brain is actually the same thing, just flip it over. Yes?
Why do you know that endo versus exo is not an issue?
Because I have no way of distinguishing the groups that are inside versus outside because they are hydrogens. I can do it here with colors, but chemically I can't. Yep. Now, another issue, stereospecificity. Let's do the same thing. Let's have, we'll use the same diene, but in this case, let's use a different dienophile. Let's have the olefin be trans. Again, I know that endo and exo are not going to be an issue this time for two reasons. First, because I can't distinguish between the inside protons and the outside protons. And second, endo and exo are only easy to assign when the groups on the dienophile are cis to each other. When they're trans to each other, you can't choose endo versus exo. I'll illustrate that briefly in a second. So if I choose one of the two pink groups on the dienophile to be a wedge, the other one has to be a dash. They have to be trans to each other. Now it turns out that that product is chiral, but our starting materials were not chiral, so we have to get the other enantiomer too. We can get that other enantiomer by chance in a couple of ways. You could get it by having the dienophile approach the diene from the other side, or you could actually flip the diene over. Now, I wanted to illustrate just briefly why you can't choose endo and exo when the molecule is, when the diene is, or sorry, when the olefin is trans. So I'm just going to briefly modify this example and imagine that this was cyclopentadiene. Do you see that when we can identify a group that's on the inside, which pink one is the one we're talking about when we say it's on the same side or opposite side as the blue one? I don't know, you can't. So if your olefin is trans, you don't have to worry about endo versus exo. Yes?
Does that include when one of the groups is maybe heavier than the other?
Now, what if one of the groups is heavier than another? Could you establish some sort of priority system and decide which one to talk about and therefore get endo versus exo? You could, but we won't care. Yep. Okay. So let's do some retrosynthesis now. There are more complicated Diels-Alder reactions than this on your problem set. I encourage you to do them and get used to this. But we need to now do a little bit of retrosynthesis. So let's choose some challenging examples. So the question would be asked in this way: what diene and what olefin did you need to synthesize this product? There's the double bond. Okay, so the first thing that's going to happen when you look at this is you're going to panic and say, what even is that? Yeah. So, after you take a deep breath, focus on looking for a cyclohexene ring. Try to identify 6 carbons that have a pi bond in the ring. I find one right there. If it's hard for you to do that, you could consider redrawing this molecule as it would appear from above. You've got the sort of blue bridging atom here that's a wedge. You have a pi bond here. Then I've got a chloro and then an oxygen with something else on it. Okay? There is the 6-membered ring. Now, once you've identified the cyclohexene ring, you're almost done. Find the double bond. That double bond has to be carbons 2 and 3 of the diene. Then if you can count, it becomes clear that these 2 carbons must be 1 and 4. We're relying on what we know to figure out what we don't know. We know that in the Diels-Alder reaction, we actually form new sigma bonds involving carbons 1 and 4 with 2 separate carbons of the diene. And that makes these 2 carbons 1 and 2. Okay? So now, thinking backwards, I'm going to draw the diene by, conceptually in my mind, breaking the sigma bonds between orange 1 and purple 1 and between orange 4 and purple 4. So I'm going to just draw the diene. Pi bonds are going to be between orange 1 and 2 and between orange 3 and 4. Of course, blue group still has to be there because it wasn't involved in the reaction. It's just hanging out there. So that's my diene. Now, how about my dienophile? I simply draw carbons 1 and 2 of where the dienophile must be. I put a pi bond between 1 and 2, and that's it. Everything else stays exactly the same. Now, fortunately, in this example that I chose, there was no stereochemistry to pay attention to. There were groups on carbon 1, but no groups on carbon 2. However, had there been groups on carbon 2, you would need to make sure that you got the stereochemistry right. Cis groups in the ring have to be cis in the original dienophile. Okay? You need to practice that. And there are tons of examples on the problem set and at the end of chapter 12 that you can do. That is it for today. Good luck on the exam. I will see you Friday.